Hello to this session. Today I will be talking about the TeraFlowSDN community. So you can observe here that the networks have become more complex. Then this means that we need an SDN controller for handling this complexity and this dynamicity. You can observe where we're placing TeraFlowSDN in between the cells and gateways and the core network. That's our location. So we are providing transport over different kinds of routers, IP layer 3 routers, and also DWDM networks. So that's how we see, and we provide northbound interfaces towards the OSS, BSS through the layer 2 VPN services, also towards the OSM, for example, to the NFV-MANO, and we also provide southbound interfaces. So this is how we relate to that, so that with these southbound interfaces, we're able to configure P4 routers, open config routers, transport API, and so on. But with this, we provide a lot of complexity, and so we are handling this with our cloud native approach. This means that having a transport SDN controller, which is cloud native, brings us a lot of benefits, such as, for example, the self-healing properties, automated rollbacks, auto-scaling, and load balancing. Well, there are other challenges that we also need to tackle, because it's very important that with this distribution there are challenges, but I will not enter into details. So here we can see that how ETSI TeraFlowSDN is based. So we are an open source community. We focus on IP over DWDM cases, also cloud native SDN controller. We are compliant with European cybersecurity requirements. We are community driven, and we are aligned with the mass requirements. So we don't want to do standards. We use standards. We focus on operator use cases, and we are part of a global community.
And that's it for that. So that's outdated. I must say that we have many people joining. Every time I need to update this, I'm showing this slide is outdated because we have a lot of people jumping in, and we are starting to see people from outside of TeraFlow jumping in. So that's very good, and we are welcoming everyone's contribution. So that's what TeraFlowSDN is. We see it as a toolbox for rapid prototyping and experimenting the different network technologies and use cases. So it's something that eases the adoption of SDN technologies to the telcos. It focuses on network programmability, and we are willing to collaborate with different ETSI, ISEs in order to have the standards back to the open source community. That's our proposed architecture for second release. As you can see here, we have many different small components. The most important thing is that you keep in mind with for example, the context component. That's our main database. We have the device component, which is handling the southbound interfaces. We have the service component, which is handling the connectivity service lifecycle. And we have an NDI component that's called compute right now. That is like the single point of entry to our microservice-based architecture. So that's how this looks like. I don't want to enter into details, just to remind that we have integrated with OSM. So TeraFlow is able to be used as a WIM, as a one infrastructure manager. And we have provided some demonstration available, and also we have contributed to provide this interconnectivity. So I think that now is Lluis' turn. So thank you very much.
Okay, so let's start with the first exercise related to the TeraFlow controller. The idea of this exercise is that you should be able to deploy the SDN controller. It's the first step, hacking or playing with it. So for that, we prepared the virtual machine, just in case you need to deploy TeraFlow SDN controller somewhere else. The minimum requirements that we are considering right now is to use Ubuntu 20.04 LTS operating system, even server or desktop. We are usually using server for obvious reasons. Then it's recommended to use at least 4 virtual CPUs because with less, some services might have trouble. At 100% execution capacity, 8 gigs of RAM, and something around storage disk. With this, you can compose virtual machine for running TeraFlowSDN control. It's pre-built for that. But if you want to reproduce how we built the virtual machine, you have the tutorial ETSI GitLab repository. And in principle, you can follow the steps in kind of a walkthrough manner, and it should you should be able to reproduce this virtual machine well for the server part, because also then you need to install the desktop part. Next, and before continuing, I want to stress a couple of comments because many people that is trying to deploy TeraFlow sometimes is not doing a sanity check. It's not about the deployment of TeraFlow. It's about the use of microcades. It's very simple. It's that before starting to deploy TeraFlow, please ensure that the add-ons and the status of the microcades environment is up and running. Because if you start deploying TeraFlow and the microcades is not ready, you might find unexpected scenarios. So it's better to use these commands. I will show you in a moment which is the expected procedure. And also you can use these commands during the Hackfest or when you are playing with TeraFlow in case you need to check which is the state. Okay, say that. The first thing I want to explain is that we tried to facilitate as much as possible the deployment of the TeraFlowSDN controller. That means instead of having to tweak a lot of files, we tried to compact the settings in a single file that you can source. It's a bash script that you can source, and it provides well the different settings. These settings are the Docker registry where we will store the produced images for the different microservices. In here, in the default deploying settings, that is this my deploy.sh script, it's already in the repository. We are considering to use the internal microcades Docker registry because it's a simple way to and it's quite fast to use. Then we have an important setting that is the list of components that we want to deploy. That means we don't need to deploy all of them every time. If we have some particular needs, we can choose what is really needed. There is one, well, I will say 2 components that are obvious that should be deployed always. It's the context and the device, because the context is the database that stores all the contextual information SDN controller. The device is the source-bound interfaces, so it's always needed. Automation is the component that deals with activation of the devices. It deals also with onboarding of devices, so it's convenient to be deployed. Monitoring, it's not playing with monitoring, you can skip this component. Path computation, it's needed for the service and the slice components. So if you are deploying service, which usually is needed, you will also need to deploy by now the path computation. Service, it's for managing the implementation, the establishment of connectivity services. A slice that provides a way to define transport network slices supported by means of service. So if you are using slice, for sure you will need service. And then the NBIs and the web UI. Compute is the NBI that enables for instance, to use open source Mano with TeraFlowSDN. And the web UI provides it's a simple graphical user interface. We are trying to keep it simple in purpose because it's easier than to use, and we will use it later. Then we can define which is the image tag for the Docker images that are created during the deployment procedure, the Kubernetes namespace we want to use for our deployment. Then we can provide extra manifests that we want to deploy in Kubernetes. Here, for instance, we use the Nginx Ingress HTTP controller. It's because this definition enables to configure the ingress that is used later for reaching the web user interface, the Grafana dashboard in case we are using monitoring and so on. Also, some debug endpoints that are available in the web UI. Also the NBI for OSM and so on. And then if you are using Grafana for plotting the monitoring data, you can set the admin password you want to use. Okay, having said that, let's go for the deployment. The deployment, it's 3 steps. I mean, the first one can be avoided. It's just a matter of pointing to the right folder. Then we need to source this mydeploy script with the parameters for the deployment, and then you just need to run the /deploy.sh script. And it will trigger the whole procedure. You will see the log with the different steps that are being done. And whenever it is done, you will see a summary of your deployment. And well, that's what we will do right now. So let's start. First, well, let me close the previous terminals. Let me show you first, very quickly, where there are the scripts that we will use. First of all, mydeploy.sh. This is the script I was mentioning to you that you need to tweak. If you need a particular deployment, just copy-paste this file, tweak it the copy, and that's it. And this is the deploy.sh is the script that actually performs all the operations using the settings that you specify in the other script. So this is the script that we are tweaking as TeraFlow developers when we need to change the way we deploy. And mydeploy is where we collect the parameters for the people that is deploying the TeraFlow. Okay, let's start. Terminal. First command to run microcates status to check which is the status. It's not running. It's done in purpose. So we first start microcates. The password it's for the TFS user, so the password is TFS123 by default. We have to wait a few seconds while microcates starts. Okay. Should finish in a moment. Okay, we are done with this. First, let's run the commands I was mentioning to check. To check the status. So here, if you want to copy paste, they should be here in the commands.txt file. You can go here to the TeraFlow deployment. First, we check paste, enter. Okay, here we can see a number of things. First one, microcates is running. Okay, good point. Second point is which are the enabled add-ons. Here we need at least the registry for obvious reasons. This is the one I told you in the default deployment script. We are assuming to use it. The ingress, because it's the ingress point to reach the different components through the web through the HTTP-based interfaces. And then, well, storage, our dependencies, and so on, and the DNS of add-ons. After doing that, we need to check the status of the Kubernetes. So the components that are deployed. We are checking here all the namespaces. You see that right now we have all the stuff about system. Everything is running. Okay, it's expected condition. And also, if you want, and let's go step by step. And then the next step is right folder. So no need to run this CD. We can jump directly to the source. Here we can paste the source. Okay, we should have now the settings, and now we can run the deploy.sh. Paste here, and okay, first step is to delete existing TFS namespace. If it's already created, then recreating it, and then it will go component by component among those that were specified in the TFS components environment variable in the mydeploy.sh, and it will perform a number of steps for each of them. First, building the Docker image, then pushing the image into the Docker registry. Then it will adapt the manifest files that are provided with TeraFlow to the parameters that you set in the script. Next, it will deploy the component. And finally, it collects a number of environment variables that are collected in a separate script. I will show you in a moment when it finishes. And these environment variables are useful when you need to run, for instance, scripts from outside Kubernetes, because it collects the IP addresses and the ports that are used for the microservices. So it's a matter of facilitating the thing of running experiments and developing things. Then it deploys the extra manifests, in this case deploying the ingress HTTP controller, and we have a number of waits while the different components are being deployed. You see here that it waits until the condition is met. So for all the components, we should see that we have condition met for each of them. And the last step, in case we configure it to deploy the monitoring and the web user interface, there is a step that configures Grafana to use the monitoring database. After that, we will get the report of our deployment. Expected result is to get everything running, and 1/1, 2/2, depending on the component. So everything went fine over here. And also we got the ingress controller. That's good. In case you want to reproduce this final report, just show deploy, and you should be able to get it. Yeah. Okay. So if you haven't done it, you can try to deploy the TeraFlowSDN controller now. After that, the next step I will propose to do is to open Firefox, and then if you point to 127.0.0.1, it's port, well, that's it. You should get not found because we need to add here the web UI, and we should get access to the TeraFlowSDN web user interface. In this web user interface, it's, as said, it's very simple. We have a home page with a couple of forms. The first one is to select the active context. Right now we have no context created. We will create one in a moment. And then we have the upload JSON descriptors. I will elaborate on these descriptors in a moment. It's a way to onboard configuration settings into the SDN controller. We can see the list of devices. Since we have no context right now, it's just pointing back to the same page. The links, the services, the slices. We can open the Grafana dashboard, but we will not use it by now. And then we have the debug tab, where we can get some debug information over here. So for instance, you can see the content of the database. Right now it's empty. So let's go back to the slides. We are done with the deployment. Now let's go for onboarding the devices. For that, we will use the JSON descriptor files that I was mentioning. These descriptors are, as I say, JSON files where you can specify which entities you want to deploy. We have a number of basic entities. First, the context, then the topologies. These are the two main ones. You have example files in this folder of the virtual machine. First, let's onboard the context and topology. So for that, let me jump into the virtual machine. I will click here on Browse, File. Here in the TeraFlow SDN controller, Hackfest, TFS descriptors, we will choose the context topology and submit. Expected result is to have one context and one topology added, well, updated because it has a second step. And after doing that, here you should be able to select the context. So we can select here admin, submit. Now the current context is admin. And if we go to the devices, links, services, slices, everything is empty. Okay, it's normal. So let's go back to the slides. Well, it's kind of an exercise, so I invite you to deploy the TeraFlowSDN controller if you haven't done it. And what I will do now is explaining the descriptor file for the devices, for onboarding the devices. Then the exercise will consist in you need to start again the TAPI server that we were using in our previous exercise, and using, well, this example descriptor, you should be able to onboard the TAPI server as a controller, abstracting a wall topology. That means we will just consider the service interface points here, not internal details of nodes, links, and so on. So the descriptor for the device contains the essential information settings that needs to be provided for each device. That means the device identifier, in this case we are using OLS, the device tape, it's an open line system in the case of a transport API server. You can check the list of device tapes that we are supporting in the source common device tapes. It's in the virtual, it's in the virtual machine. Here in the source folder, if you go to common, you can go to device tapes, and here you have the list of device tapes. Okay. Then we need to specify a set of configuration rules. These configuration rules are those used for configuring the device, and in particular, when we onboard a new device, these rules are those used for connecting to the device, or in this case, the controller. For that, we need to provide at minimum the IP address and the port, and then depending on the driver we use, that is chosen based on the device tape, the driver might need other settings. As an example, if we want to use a netconf server for managing the device, we will need to provide the username and password because it's using SSH. So in this case, OpenConfig, we will tackle OpenConfig later. To be used with, to use the netconf, we need these two settings. Then we need to provide which is the initial operational status of the device. By default, disabled. It's this one here. You can check the proto context.proto file. In particular, you have the enum specifying the list of operational statuses. The driver we want to use, in this case, 2 means transport API. And then the device endpoints by default should be empty, because when the driver is started, it will contact the device and will discover which are the available endpoints. Okay. So yeah, the expected result for this exercise should be that you get an OLS a device named as OLS with tape open line system and so on. So here I will give you maybe a couple of minutes to do that, and then I will do it by myself. Okay, so let's try to do that. I will do it by myself. So first, a new terminal, and I will go to the Hackfest Transport API server folder. From here, LSLA, I will run the server. Okay, it is starting. We have the server up and running now. And the next is going here, and if we find the device TAPI OLS file, I will show you first this file. It's here in TFS descriptors, TAPI OLS. You have the settings, well, the descriptor I was explaining before. Okay, so we choose the file, open, submit, and in few seconds we should get a message saying that the device was contacted and onboarded. Okay, one device added. Now if we go to the device, you can see device OLS. Right. Something went wrong. Something went wrong. Just a second. Let me check. So scripts. If we have it here in the scripts folder, there is a set of useful scripts for testing. So for instance, one of them enables us to check the logs of the different components. In this case, I will check the logs of the device component just to see what happened, because maybe there is something wrong. Okay. Let me check IP address. I guess I have a mistake in, yes, mistake in the IP address in the descriptor. The virtual machine has the IP address 10.0.2.15, and my descriptor has the wrong IP address, so sorry. Let's retry. I just updated the descriptor file with the correct IP address. Here, I will go here to the devices. I will go here to delete device. Yes. Okay, deleted successfully. Let's onboard again. Submit. Added. Okay, now I have the device here. Oops. Device. Okay, and I have here the OLS device, open line system with the list of endpoints, and using the transport API driver, and the status is enabled. If I'm going into the details, I can see the tape of the different. Hello? Okay. So we can see the list of the endpoints here, and also the list of configurations. Here the configurations are just specifying that the endpoint exists in the device and the tape they have. Okay, so nothing surprising up to now. So well, That's the idea. I was mentioning this point that in case of trouble, you can use the show logs scripts to check what's going on. And with that, we conclude this exercise on deploying the TeraFlowSDN controller and also onboarding a simple device. Everything clear, more or less up to now? Okay, let's continue with the next part that is about programmable layer 3 routers with OpenConfig. So OpenConfig is another data model that is used for managing network devices. It's the idea of the OpenConfig is that it brings a number. We have the data models that provide information on the status and the configuration of the devices. It has also a set of data models that are for telemetry streaming, so we can get monitoring data in real time. And then we have a number of remote procedure calls that can be used to implement operations to be performed over the devices. As an example, for instance, we could have an operation to reboot a device. Okay. Then OpenConfig, it's huge. I mean, it has a large number of models inside. So we can see here, well, it's quite small, but there are a number of models, for instance, for managing network instances, routing policies, routing authentication, BFD, interfaces, layer 2, the platform. Here, for instance, we can find the components of the physical device, system management, access control lists, and well, and so on. In particular, there are others for optical transport and for Wi-Fi. Okay, so we have a lot of models on in OpenConfig. Then these models, the idea is that well, are modular and simplify the management of the devices by organizing the information in general into blocks for each particular functionality. So one of the blocks is about the configuration, and the other is about the status. So that way, you can always see which are the settings that can be changed and the status of the component, not only with the configurations that is running, but also the status on some read-only parameters. Okay, so for instance, you can, I don't know, as an example, a read-only field could be the number of ingress and egress packets and bytes for a specific network interface. You cannot configure anything on that. It's just a status of this particular component of the device. Okay. Besides that, well, it's driven by versions. You can have different versions for the OpenConfig data model, and depending on the device and the network operating system that you are using, it can implement one version or another, or even a number of different versions. And then it's the network operating system that decides how to configure each of the operations depending on the version that you are using and so on. Okay. So you can see here a small example on BGP networks, which is the aspect of this kind of trees for OpenConfig, for instance. Here I'm providing some examples on the OpenConfig data models that we are using right now in the TeraFlowSDN controller. About the OpenConfig interfaces. So these are the fields that we need to manage at minimum to configure the network interfaces in the layer 3 routers. If you check here, you can see that for each interface, we need to specify which is we need to know which is the name, the tape, the maximum transfer unit, descriptions, the status, if it's enabled or disabled. Then we can monitor, for instance, the ingress and egress octets packets when and a lot of other fields. I'm here just summarizing some of them for illustrative purposes. And then for each interface, we have sub-interfaces, well, with the appropriate fields, in particular the number of sub-interface within the interface. And again, it's the status and so on and so forth. We have here, again, the counters for the sub-interface. Then, in case we want to manage, for instance, virtual LANs, and we need virtual LANs identifiers, there is an augment that is named as VLAN that extends the OpenConfig interface and sub-interface models appropriately to handle the different VLANs. And similarly, if we need to configure layer 3 IP addresses, then we can use the interface IP augment to configure the IP addresses and the prefix lengths and so on. Well, again, there are large number of I'm just keeping the thing simple. Okay. Then, in case we need to manage routing policies, that's the case, for instance, when we need to use BGP, we can use the router policy model plus the BGP policy, and here I'm combining both of them. And well, I haven't said that, but in blue are the specific fields that we are. Hello? Okay. Perfect. We are back. Hello? Yeah. Well. Okay, so as I was saying, the fields in blue are those that we are using specifically in the TeraFlowSDN controller by now. And, well, using, I will say, we are changing in the devices, okay, to implement the different functionalities. So, for instance, if we want to implement some policy rules for managing BGP, we need to specify in the BGP defined sets, which are the external community names, members, and so on. We need to define the policies, from the name, the statements, and the different conditions and actions that needs to be implemented. And for the blue fields, here I'm providing a couple of examples of which settings might be needed to establish. I haven't provided for the interface because it's quite obvious, but maybe for this one it's convenient. And you see here that for my instance, imagine that we have a network instance that is named as my instance. We need to specify some import rules. For instance, for the root target 65.0.0.333. And in particular for that, what we want is to install protocol for direct connected, and we want to accept the rules. Similarly for export policies, okay, just as an example. And then for the network instance, again, we have a lot of fields. And here we are combining the two previous, the settings in the two previous models to associate a network instance that is like a virtual virtual router. We specify which are the policies. These policies come from models that we were setting beforehand. We can specify also encapsulation. We can also specify, for instance, the tables for routing and how the different involved protocols are exchanging information. And also we specify which are the interfaces and superinterfaces that are part of this network instance. Okay, more or less clear up to here. Then, how everything is combined. Here, I'm depicting the workflow that we implemented inside the TeraFlowSDN controller. Extracted from one of the internal milestones that we have in the project. And the idea here is that when the external system wants to create, for instance, a layer 3 service, or slice. It issues the request to the compute component. Then from the compute component, a slice creation request is sent to the slice component. Slice component indeed creates a new service. And then for the service, first, it interrogates the path computation component with the service details to discover or to compute which are the connections, subconnections, and so on that are needed to implement this service. With this information, what the service component does is to go subconnection by subconnection. In this case, if they are using transport API for the device involved, and sending the appropriate configure device request to the device component to configure through the OLS SDN controller the devices. This part is out of scope, to don't invest a lot of time. And then for the other connections, what we are doing is for each of the connection, for each of endpoint in the connection, we are configuring the device. In particular here, if we are using OpenConfig, and this configuration implies first configuring the network instance, then we need to configure the interface, we need to configure the sub-interface, we need to configure the interfaces associated to the network instance, we need to configure the protocols associated with this network instance, we need to configure the table connections associated with the network instance again, the routing policies, the BGP routing policies for ingress and egress, the policy definitions, then we configure the inter-instance policies. Well, all of them are details about the network instance and routing. And then, well, here in this case, it's because in this workflow we were using LACP and also MPLST. But it's just to illustrate the kind of workflow we need to follow. I mean, I was mentioning before that here for the network instance, for instance, we have a lot of fields. In general, we cannot set all of them in a single shot. We need to go step by step. Because, for instance, if we have not, to see here some example, if we have not defined, for instance, the protocols, we cannot configure the connection tables. So it's like one depends on the other. So you need to go step by step. Okay? And well, for the optical transport, for the sake of saving time, maybe I will go quite fast here because it's just some details on the terminal device model that is used for modeling devices, in particular here, things related to the terminal optics, the wavelength routing, the optical amplifiers, channel monitoring, and so on. So the idea is that the data model enables us to define all these settings with different technologies, with the different wavelengths, modulation formats, and so on. This is just an extract of the data model. Here you can see, for instance, representation of logical channels. We can see here, for instance, different read-only information on the status. You can see here like forward error correction ratios, bits, and so on. And well, it's more about the terminal device. Maybe we can skip it. And well, even more. It's just to illustrate that here, for instance, we are extending different parts of the original OpenConfig model. In this case, for instance, we are extending the component with information about the optical channels. Okay, so let's go for the next exercise. The idea of this exercise will be that you will onboard a netconf OpenConfig server that we prepared. It's a very basic network OpenConfig. It's not implementing the entire model. I will say it's just a simplistic subset for the sake of this Hackfest. It's already provided. You can see that in this Hackfest netconf OpenConfig folder, you have the server openconfig.py. Remember to set the port where we want the server to be listening. In general, we will be using port 8300, and then in another exercise that we will be deploying a number of these servers, we will change the last 0 by 1, 2, 3, 4, depending on the number of the device. Okay. If you are curious on how this server was built, you have in that folder a specific field named as build instructions that you can check, and it explains more or less how it is implemented. Okay, and here, it's just a similar slide like the other one for the other exercise that we were using for onboarding the other device. Before jumping here, let me go to the virtual machine, and we can start in few seconds the netconf server. You see here we have the server openconfig. The script is quite simple to the other one we had. It's just that here we are providing a different way to define the internal information. So instead of having an XML file as we had before, here we are using this get device definition method. And this device definition method, it's here. It's using PyYangBind in this case. We are taking the openconfig build scripts. These are built by means of the PyYangBind, as we were doing for the topology and the connection. You can check here the internal details of how these files were generated. I don't know, here if you go to the init, you can see how it's implemented, in particular the openconfig components node. So you can see here the components class with the different information. All this code is automatically generated by PyYangBind, so might be kind of hard to follow, but just for your information. Then, as said, we have the server. This server defines the data that is exposed by means of this method. And in this method, we are doing very, very simple device model that contains components and contains interfaces. Components has 3 ports, okay, and interfaces is empty, just for the sake of this example. And then we are combining them within the netconf data tag, okay, or element. Then, to start this this server, well, we have here the transport API. Maybe we can open another terminal. We can go here to the Hackfest openconfig, and from here we can just run Python. I guess I have the command here. Yes. Okay, let me copy here. Oops, lost the virtual machine. Here. Okay, so if I paste here and run, we get one netconf server up and running. And now you can try using this this descriptor to onboard this specific device. So you have again the description of the different fields. I will not stress it so much. Just a matter of setting the appropriate IP address, port, particular. And that's one change for the people in the TeraFlow project. It's something that we were discussing some weeks ago, that it was kind of boring because this settings field previously was a string and it was hard to compose. Right now, you can use a dictionary, so it's easier and less error prone for defining. So this is the set of settings that are required for the openconfig the OpenConfig driver in TeraFlow. Okay, so it's just a matter of copy pasting this block, and it should work. You have also the the TeraFlowSDN descriptors for this netconf here in the OpenConfig. So it's the same file that I was showing in the slide. Remember to change the IP address. Check the IP address that your virtual machine has, because otherwise it might fail. So to onboard, and if you succeed with that, you should get a web interface with the router onboarded, and you can check the logs if you want. And after that, we will. I propose you can do it everything in a row. Well, the links can be defined again. So here you can provide a name for the links. You can provide. You need to provide the endpoints of the link. So if we have two routers and we want to connect them by means of port 1/1 of each of them, we will put here router 1, router 2, and then here the respective endpoint identifiers. Okay. For the service, we can do something similar. It's a bit more complicated, the model for the service, but it's essentially putting here the context identifier, the service identifier, the type of service, the initial status of the service, and the endpoints of the service, and then some constraints and configuration rules. The exercise I propose to do, it's about onboarding an entire topology here. The idea of the topology will be that we will have 4 netconf OpenConfig servers running. That means instead of 8300, we will use 8301, 8302, 8303, and so on, and the TAPI server that we already have. Then you need to create the descriptor files for onboarding all these devices, or at least you don't have in your environment. Create the definition for the links that we want to onboard. You have here a summary table with the names of the different endpoints for each of the devices that we need to use. And if you succeed, you should topology in the main page of the here. So instead of a single device, you will get a topology with 4 surrounding routers here. And if you reach this point, the next step is to onboard this service layer 3 VPN file. So that way you will create a service, and you will be able to see in the service entity which is the aspect of the service, and you also will be able to check the configuration rules that were created for each of the devices. Okay. For that, I guess with 20 minutes it should be enough for doing that. So I propose you to start working on that, and if you have any trouble, let me know. Okay. Okay. For the sake of time, I will show you now how this thing of the layer 3 VPN service creation works. So the idea is that we will need to run this set of commands in the terminals to start the different TAPI server and netconf OpenConfig server. So let's do that. I will go here to the virtual machine. Let me open the thing. Oops. Okay, so we have the TAPI server that is already running. Here we have one netconf server. I will remove this one because I will use the descriptors file that I have, and it has. Oh no, okay. I hadn't onboarded. Perfect. So that's it. I will start it with port 1. I will create another one. Let me copy here this path. So cd. I will create all the terminals now that I have the command. Okay, then here I will start copy. I will start second netconf openconfig server, third netconf openconfig server, and the fourth one. So we have now the different devices. We have a file that is defining all the devices here. It has, well, it's the solution for this. It has the router 1, router 2, router 3, router 4, and the OLS. In this case, since the OLS is already deployed, I will just remove this one to go fast. Save. So now the device all is including the missing devices. So home. Here I will onboard these all devices. Okay. Submit. And in a few seconds, okay, 4 devices added. We see now that we have the 4 routers and the OLS. We can check here in the device tab the 4 routers. All of them are active using openconfig. They have the same set of ports because we did it that way. And I have also here the descriptor for the links. So you can see here all the descriptors created for the links that are in the table that I was showing you. Let's go back here and onboard the links. Okay, submit. And now we have the topology. We have the OLS in the center and then the 4 routers. Next step is to create the service. As I was saying, here we have the service layer 3 VPN. With all the details, we are creating a connection between router 1 and router 3, interfaces 1/2 in each case. The identifier of the service will be network X layer 3 SVC. And we are defining here the constraints in terms of bandwidth, latency, and also some settings about IP addresses and routing stuff. Okay, so let's onboard this descriptor, service layer 3, okay, submit, and in a few seconds we should have it. Okay, so now if we go to the service tab, we have the NetworkX layer 3 service created is layer 3 network management between router 1 and router 3. It's active. We can jump into the details. We can see here the constraints that were defined for this service. We can see the configuration rules. We see that we have configuration rules for the in general for the service and other configuration rules that are specific for each of the device endpoints. And also we can see the list of connections and subservices that are created for supporting this service. In particular, since this service is traversing an OLS, that is an optical controller, we need to create a subservice for the transport API. So here, the service is supported by a connection that is passing through router 1 and router 3. And here, in the jump between router 1 and router 3, we are going through the OLS. So here, it requires a subservice. If we go into the details of the subservice, it says that we are connecting node 1 port 15 with node 3 port 15. We have the details, it's in the photonic media. Then we have the connection that is going from one OLS port to the other. So here we go back to the services. We have everything. And we can check also in the devices. For instance, I will go to the OLS. And here you can see that a service was created and, for configuring this connection with all the attributes. And also going to the device list, we will check just one of the routers, and you can see that here it created the network instance. It created, for instance, interface configurations, subinterface configurations, association of the network service with the interface, and, well, protocol, BGPLS, the table connections, all the details. So that was done just by did the rest. Now we will delete this service, so we will go to the network X layer 3 service. We go to the detail, we press the delete service button, yes, and in few seconds it should delete this service and the rest of entities that were created to support the service. You see, now we have no services, and in devices, if we check, for instance, in the OLS, we have no service created here, okay? So that's to conclude this, this exercise. And the last exercise that I want to show you, it's pretty simple. We will be using the same network topology. The idea here is that we will use not open source Mano. We will use a mock open source Mano application. It's a small application that we use for simplifying our experiments when we are doing the test and the development. The idea is that open source Mano, it's based on a number of components. In particular, one of them is the resource orchestrator. And this resource orchestrator has a number of connectors for one infrastructure managers, like the TeraFlowSDN controller. What we did is to extract a very, very minimal set of files from the open source Mano for the specific IETF layer 2 VPN connector in a way that we can trigger the same message that open source Mano will send to the TeraFlowSDN controller to create, in this case, a layer 2 VPN service. These files, if you want to see them, can be found here in the mock OSM folder. And well, if you check, you will see that this file is essentially the one connector IETF layer 2 VPN file. This is copy-pasted from open source Mano, just adjusted here some import in the packages. This SDN-COM is the interface that defines how an SDN connector should be implemented. This is copy-pasted again from open source Mano. And then we have the mock OSM. This is implemented by us and contains a very, very minimalistic implementation that enables us to use this one infrastructure manager connector and trigger the creation, the get service status, edit service edit connectivity service, and delete connectivity service. So it's very simple, but the good point is that it mimics exactly the messages that we will receive from open source Mano for testing TeraFlow. And then it works because it's then we are using TeraFlow with open source Mano in big real experiments, and then it's a good way to verify the integration. What we will do now is to use this mock OSM to reproduce this scenario. So we will reproduce like we were trying to interconnect two different sites, each of them having a specific virtual infrastructure manager that is in theory managed by OSM. We will not be handling this part here. We will just focus on the network, the transport network, okay? So we will use here the mock OSM to emulate what OSM will do to interact with TeraFlow. So for that, we will use the IETF layer 2 VPN data model. I will not elaborate on that because it's a bit long. Just to mention that in this data model, for each different site that needs to be added, we need first, well, sorry, let me restart. When we want to create the connectivity, we need first to create the layer 2 VPN service. If it doesn't exist, then the compute component will create, in this case, a slice. If the slice doesn't have the service, it will create the service. Okay, so at the end, it will return the identifier of this slice and service to the OSM, and then OSM, for each site that is involved in this layer 2 VPN, it will add a site network access that will update the slice and the appropriate services and configure the devices. So this is the kind of message that we will be sending. And maybe we can do that, because since we are running out of time for the other part, I will show you how to do that, because it's quite simple in this case. So we will first open a new terminal. We will go to the Hackfest. And from here, we just need to run Python -m mock_OSM. Okay, we are in the mock OSM. You can type the help command, and you will see the list of commands that you can use. Very simple. Creates the service, deletes the service, and status retrieves the status of the service. So if we type help create, it's very simple. It has no parameters. So it's everything by default, just to simplify things. We type here create. And if we go now to the TeraFlowSDN and check, for instance, the slice, we got a new slice that was created, active. If we check the details here, we have all the information. In this case, it's okay. We have here the two endpoint locations. One is in region 1, the other in region 4, because we are connecting the router 1 with router 4. We are providing here some minimalistic settings for that. We can check the service that was created. It's a layer 2 service, because we are creating layer 2 VPN. We have here the settings, essentially the same that come from the slice, and it's creating the connection between router 1 and router 4. Again, it's supported by a subservice in the OLS. It's Transport API. So we are creating the connection. Okay. So that's essentially what I wanted to show. And here, well, it created the service. We can here type status, and we will get the status of the service. It says it's active. And finally, we can delete the service. We type here delete. It will take a few seconds. And after that, slice, okay, it was deleted. Service, it was deleted. And in device, we can check, for instance, the OLS. And here we have no services. And well, if we check for the routers, again, we'll have nothing there. So with that, I mean, I was a bit fast on that, because we want to have time for the other. Here it's just the set of commands I was running for this exercise. And with that, well, this is the monitoring part that we will skip.